Hello students. So in this class we will be talking about Bose Einstein statistics. In B statistics, uh, all the quantum states have equal a priori probability. That is, all the quantum states are equally likely to occur. So if Gi is the number of states and Ni is the number of particles, these Ni are indistinguishable in nature, and they are to be distributed among these Gi states. So we have Gi plus Ni as the total number of objects. Now when we distribute, we need to keep the first state fixed. So keeping the first quantum state fixed, we have Ni plus Gi minus 1, this much of objects permitted. So these objects can again be distributed in, as you know, factorial ways among themselves. So, and again we have got Ni particles can be distributed among itself in Ni factorial states, whereas the Gi minus 1 states can be fixed among themselves in Gi minus 1 factorial ways. Okay, so if you could take a ratio of these two, what we obtain is the thermodynamic probability. For it, now this thermodynamic probability, as you can see, we have used a suffix I here. So this I actually stands for the energy level EI. Now if we have n energy levels, say, that means I runs from 1 to n, then the thermodynamic probability of the whole system, the thermodynamic probability of the whole system is W by I is equal to 1 to n Ni plus gi minus 1 factorial divided by ni factorial and gi minus 1 factorial. Now if we take now since ni and gi are very large quantities, so this can be simplified into simply by ni plus gi factorial divided by ni factorial and gi factorial. If we take a natural log of this, and then w, so we put in different color. So we take ln w. Using the Stirling's approximation. Stirling's approximation stands for, so right here, Stirling's formula. Stirling's formula says if ln n factorial is equal to n ln n minus n if n is a very large quantity. So in the same notion we can write ln w, it actually comes out to be ni plus gi. So we will have a summation sign here. So by taking natural logarithm, this multiplication or this cumulative multiplication converts into a summation. Ln plus gi ln ni plus gi minus ni ln ni minus gi ln gi. So ultimately this is the equation that we obtain till now. Now we will use some conditions here. The first condition is that if the work is maximum, then change in delta L W is equal to 0 is the first condition, and this happens for small change in dni. And the two more conditions are there. First of all, summation delta ni is equal to 0. This is the conservation of number of particles, and delta ei ln I is equal to 0. This is conservation of energy. Using these three conditions, what we finally observe is we get the following relationship. We get ln ni plus gi divided by ni minus alpha minus alpha beta minus beta I is equal to 0, and you get the occupation index here, which is actually the ratio of Ni/Gi, number of particles per state. This we get as 1 by exponential alpha exponential beta ei minus 1, and alpha and beta are called Lagrangian multipliers. So this alpha, in fact it's minus alpha and minus beta. These two are called Lagrangian multipliers. Now theta is basically found to be 1 by kt, and so we ultimately get the expression as Fei is equal to 1 by exponential alpha exponential Ei by kt minus 1. This expression we obtain. So let us write it again. Fei is equal to 1 by e to the power alpha to the power Ei by kt minus 1. Now Bose-Einstein condensation, if we take these statistics to a very low temperature, it is much useful. It is basically a low temperature physics tool. So if we take it as a very low temperature, that means if T tends to 0, this alpha is actually also tending to 0. So then the Bose-Einstein condensation converts into Fei is equal to 1 by to the power Ei by kt minus 1. So it indicates that it actually implies at a very low temperature the particles they occupy the lowest energy. So if we have states like this, these are the energy states, for example, and the distribution of particles is like this, say. Okay. This is at a temperature which is say much greater than 0 or little greater than 0. And if we take the temperature close to 0, then what will happen? the maximum number of particles will be at the lowest energy stage. So the number of particles in the lowest stage increases. This is actually what we call as Bose-Einstein condensation. Now, for understanding, let us assume that what will happen if the temperature is very high. Temperature is high, then the occupation index will be e to the power minus alpha minus the EI, which is in fact is the MB Maxwell-Boltzmann distribution. So what we can infer is that at high temperature the or MB or B is actually one of the or we should say MB distribution is one of the cases of the B distribution. So similar to an MB and B distribution, what we have is an Fermi-Dirac distribution. Fermi-Dirac distribution is, again, we have got GI states and Ni particles. Now the difference between V and LD, in this case the number of states are much greater than the number of particles, and the particles are extremely small. So the thermodynamic probability in this case, as GI states can arrange among themselves in GI factorial ways, and Ni states can arrange, Ni particles can arrange themselves in Ni factorial ways. So the thermodynamic probability for energy, for the ith state energy, that is Wi, this actually is GI factorial divided by Ni factorial into GI minus Ni factorial, which on simplification, exactly as in the previous case, this what we get as the occupation index FEI for Fermi-Dirac statistics, that is Ni by GI, we obtain an expression 1 by e to the power alpha to the power EI by KT plus 1. So instead of minus 1, as in the case of V, we obtain a value plus 1. And for the Fermi-Dirac statistics, this alpha is actually equal to minus EF by KT, where EF is your Fermi energy, which is the highest occupied energy level at absolute zero. So the final expression for every statistics is 1 by to the power EI minus F by KT plus 1. T plus 1. Now, what are the examples? What are the particles that follow this B and MV statistics? So let us try to understand. As we have already seen that B statistics are followed by particles which have integral spins. So that includes photons, phonons, and also Cooper pairs. Cooper pairs are doublet an electron pair, which is the sole reason of superconductivity taking place. Other examples of B are pi mesons, alpha particles, deuterons. Okay. Similarly, FT particles or particles following statistics are your electrons. Then we have positrons. We have the nucleons, that means neutron and the proton. Then we have the helium nucleus, and we have mu mesons. These are the particles. These are the particles which actually supported the statistics. Now, to recapitulate, the difference between FT and E is BE. It follows Heisenberg's uncertainty principle, but is unable to follow Pauli's exclusion principle. Whereas FT, so this is a crosshair. For FT, it actually follows both of them. So what it actually implies, what it actually means by following or not following these two principles. So let us try to understand. So if we have, say, two states, let's say we have three states, and we have three particles. So let's name the states as 1, 2, and 1, 2, and 3. And we have three particles. So let us say we have two particles A and B. So remember that a B is in a B, you will not be able to distinguish between this A and B. So for a BE, instead of having an A and B particle, what we will have is an A and A particle. So you will not be able to distinguish between these two. And since it doesn't follow Heisenberg's it doesn't follow Pauli's distribution principle, so you can have either a single particle in each state, or you can have both the particles in the same state. Had it been three particles, then for the B it would have been AAA, and it may even so have happened that we may have three particles in a particular state, or it may have AA particle in the down and in one state, and we may have two particles in the state. So anything could have been happening. So the probability of distributions is much higher in the case of B, since it is not following the Pauli's exclusion principle, and also the particles are indistinguishable. But for the case of Fermi-Dirac, which actually follows both the principles, so A and B, or let us put as C, they remain as A, B, and C. You can actually physically distinguish between these three. And according to Pauli, there cannot be more than one particle per state. as no two subatomic particles can have all the four quantum numbers. That means that each state can have only a one particle, so it will be A, B, C, or B, A, C, and whatever. So the number of probabilities or the number of distribution in case of FD is much less compared to the number of probability of distribution in the case of B. So this is actually the difference between an FD and a B.